tools. And then just to build the PEM library itself. The PEM library has no knowledge of any events hard-coded in it. It's completely only specified in the event specification. So again, all event knowledge is generated, the code that needs event knowledge is generated through the PEM tools. And then finally the agents. Again, we don't want to hardwire event knowledge semantics into the agents. Again, we generate these through the tools. And then the third component is now the actual implementation of monitoring, and that we implemented in a library, currently on the K42 operating system. Somebody mentioned that already yesterday. It's an exploratory operating system developed as research, which provides a really good prototyping environment for us. We have a platform-independent API, as I mentioned, to control the kind of monitoring and also the kind of aggregation that we want. So for the online consumption here in a CPO agent, you cannot just generate all these events. We'd like to directly aggregate it and only communicate aggregated information to the agent. So that is implemented in the library. Okay, so far, I mean, the library again is everything that happens here on this level is platform independent. The library itself hides all the platform-specific details, and by having all the events specified outside, it doesn't really matter. We are free to exchange and add new layers in here. And specifically, we can both run on the hardware, also on a simulator. It doesn't really make a difference to the rest of the system. And the simulator path is interesting in exploring new events and new hardware structures. So the way we envision seeing this as an exploratory infrastructure is that initially we're looking at an application, we get a first understanding what is going on, we're looking for performance problems, and then go through the monitor path and exploring different solutions, and potentially different hardware solutions. What is the effect of adding new hardware, or also new monitoring functionality? What does this bring us? So we have this currently running on both on GPUL hardware and on the hardware simulator, Mambo, which is an IBM tool. Okay, just a few words on running this. So far I mentioned we built this on K42. But we can implement the library on other systems as well. We currently have work going on supporting the library on AIX. And actually, currently without going inside AIX, so here we'd like to integrate existing tracing infrastructure. A lot of software layers, especially middleware, have their own instrumentation already in place. So we don't want to require going back in, add new instrumentation to conform to our PEM interfaces. So instead, we're building these wrappers around existing infrastructure, monitoring infrastructure, to feed and integrate the information into PEM. And I'd like to make more of a point of why the integration is so important with the example in the end. We really can correlate events that are happening in the system. Okay, so now, as I mentioned, I'm going to give you a few snapshots from a demo that we've given of this tool. So this is what we've built. Implemented the PEM library, as I mentioned, on GPUL, running on the K42 operating system. And here in this demo, we're looking at one application, a scientific application, UMT2K, which is one of the ASCII purple benchmarks. It's a mix of Fortran and C. It's written in Fortran and C. And it's one of the key applications that we are looking at in PERCS, which is in the HPC space. So we're looking now, in this demo, I'm looking at events from 3 different layers. So we have a simple stack here, actually. This is native application. The events from the application layer that we are interested in are the phase markers. And this is actually, in this case, it's a loop-intensive application. So we went into the code and instrumented the outermost loops. We actually did this manually at this point, but there's nothing that would prevent the compiler to insert these markers at loop boundaries. And the purpose of this is really to correlate what are the other events, if we're looking at hardware counters, where are we in the code, and what phase of the code are we currently executing. So this really provides context information. Then we're looking at the operating system, which generates a lot of events. So we leveraged already a lot of the tracing infrastructure there already, K42. And, but for this purpose, I'm only going to show page faults, because we started looking at this for the purpose of this adaptive page size optimization that we're interested in. And then from the hardware, we have all sorts of hardware performance counters coming from there. And so we'd like to integrate these events. So here's one snapshot. Oh yeah, I should say actually a few words. So we're generating a trace now, and here we use it in the standalone offline mode. We're generating a trace with all of the events for the entire run of the system. And then we feed this trace into a performance visualizer, PE2, that was developed at research. And again, here PE2 was also built through our tools to gain knowledge of semantics of the events. So here is now one view of the entire run of the application. It's a little hard to see. I just want to give you an overall view of what's the information that we're getting here. So we have the top blue layers there are the application markers, and there are different looping depths. So we first have number 1 is the beginning of the program, then the next one is 3, that's an outermost loop that happens twice, and so we walk into the innermost loops. They're really just at the beginning of each loop, so they can easily automatically be generated. And they become more interesting as I zoom in to really see what happens in a loop iteration. Then we have here 3 layers of performance data. We have page faults frequency. So here we accumulated, we aggregated the number of page faults per 10 milliseconds in this case. And then we have performance counter data also aggregated at 10 millisecond granularity. So we have IPC and TLV misses here in this case.
So
all right, yeah.
This sort of first yellow band is?
This first yellow band, this one?
Yeah.
This is page faults frequency.
Okay, so it's good. Okay.
Yeah, page faults, IPC, and TLV. And I'm going to zoom in, then it becomes more interesting. And because coarse view, it's harder to see things. So here's a very much zoomed in view. Number 6 is the innermost loop. And so UMT2K is actually continuously running. I mean, and this can already be seen actually. So number 6 is this band. We spend all our time in the innermost loop here. We don't really do much else in this whole run. There's some initialization pass. Every time the rest is spent in the innermost loop. And that is a sweep computation in the innermost loop. And here we again have the innermost loop markers. We have page fault frequency, IPC, and TLV misses. And they see, I mean, you can clearly see there's strong periodicity at the loop iteration boundaries, which you would expect. And there's also each time at the beginning of a loop iteration, there's actually some data structure that is being loaded, and where both the misses go up and IPC goes down correspondingly. Page faults go up at this point, so you can see that these things are really nicely correlated here at this point. We also have the ability in this tool to pull out the source. So we can go, for example, our face markers. What does the code in the innermost loop actually look like? So we can click on these and bring up the code. And this is there. Here you can also see the kind of instrumentation that we've added. We simply added trace app face start. This was our face number 6 started, and we add the line and file number and the face ended. This was a fixed 6 start and end marker, so that's all in terms of instrumentation. And there you see in the innermost loop, you're calling a sweep computation inside in the core. That's where we spend the time. All right, but now going back to what we were interested in, we were trying to look at page size and what is the effect of a current page size decision. And this was actually a very nice application to study this with. The way it operates each time in the sweep, innermost sweep computation, we're allocating very large data structures, several data structures that are more than 10 megabytes large through malloc in each of its innermost loops. So there's really a massive amount of data allocated. And we ran this initially with a standard 4K page size. And this caused really a massive amount of page faults. It was really shocking how many page faults we had here in this case. We had a lot of TLV misses correspondingly also. ERAT is in a way you can think of the ERAT as a cache of the TLV. We have a translation from the initial address to the effective address in the end. And this has to do with IBM's hypervisor. We have different partitions, so we have an additional degree of virtualization before virtual memory. And this is addressed with the ERAT translation table from different partitions of the system to the actual physical address. And here we have L1 cache load misses down here. Okay, so we tried now the next thing to run this application. Yeah?
This is on a uniprocessor?
Yeah.
Okay.
yeah, it's running on one. I mean, it's running on one processor in this case. Right. So we went now.